All right. So today, what I'm largely going to be doing is just kind of replicating some plots, so we can look at our expression data a little bit better. So there are a handful of tools, a part of DESeq, a part of that package that can let you, visualize your data, right? Plot MA. I think there's also a plot count that can look at examining the measurements or the normalized read count for a specific gene. That's possible. I think there's a PCA plot, a part of the DESeq package. But I'm not really going to mess with those all that much. I mean, they're certainly easy to use, but I'm just going to use a couple other plots. So I like flexibility and control. So I'm largely going to be using a ggplot and another program or another package called pHeatmap. So back in the day, like my go-to heat map package was like heatmap 2. But then I learned about pHeatmap, and I find it to be substantially superior. So I should have made y'all download and install pHeatmap, so you also have that as well. But largely, we're going to just look at a couple of ggplots and manipulating our data a little bit to visualize our data in ggplot. So that's all I'm really doing today. Just a few figures. pHeatmap. All right, and so if we remember from Wednesday, I exported 2 different CSV files. And I exported them, so like I kind of have this tradition of like making the output files in one script and then plotting those output files in a separate script, as opposed to doing everything in one, where time gets a little restricted, right? If I have to run through the entire DESeq package again before I can start plotting, it's not I don't think it's a very good use of time. So I'd rather just output the normalized read count and the results of the DESeq analysis to report them in later, and then manipulate those data sets. I think it's just a little bit easier, especially with ggplot, and when we need data frames and things like that. So I'm just going to re-import those in. I'm going to call it norm count for the specific read count data. That's read CSV. And that's going to be normal water 15 PSU. Make sure that loads in okay. Yeah, header's true. Row names are my gene names, and this is my normalized read count data. Right, so that I'm going to have that as one variable, and then I'm going to actually have the output of DESeq itself as another data frame. DESeq water. Make sure that loads in okay. Right, so I have the base mean, log full change, and adjusted p-value. Right, those are my 3 main columns: base mean, log full change, and p adjusted. Those are my big ones. All right. So I'm going to manipulate, just for ggplot purposes, I'm going to add another column to the DESeq results that's more or less a yes or no if the p adjusted is less than 0.05. I'm just going to call that column name fig or sig. And so to add a new column, I can just use my $, and then assign a new column name. I'm just going to call it sig, and then populate that column. And this is like, honestly, some things that you'll see me do, it's not that I inherently know how to do them. I have to Google a lot of R commands because ours is kind of tricky. And so there is this if-else command. I think there's an equivalent in Perl, not so much in Python. But it's like, if a condition is met, populate this column with one thing. If it's not met, then populate it with something else. So I'm basically saying DESeq res is less than or equal to 0.05. If that's true, populate that column with yes, otherwise no. And hopefully that should work. Okay, so now whenever I look at it, now I have 7 variables in my DESeq res. And so now I have this, again, the 7th column with whether this was found to be significant or not, given the adjusted p-value. No, I've done something wrong. I've done something wrong. Done something wrong. Something's flipped. That p-adjust. There we go. That's better. Make sure that's right now. Yeah, that's better. That's much better. Otherwise, this would have made no sense whatsoever. And so I need this column, or I want this column, basically for ggplot coloring. So I can color based off of a significance. So one plot that I can kind of quickly make out is a equivalent of a plot MA, right? So that's just where we plot the base mean on the X, the full change on the Y, and then label whether the p-value was significant or not. So that's not really bad to reproduce in ggplot. DESeq, so I'm going to call the data frame. Assign my AES, right? All stuff that we've done before. My X is just going to be the base mean. The Y is equal to the log2 fold change, and color is equal to sig. And I will use a geom point for that. Okay, let's see how awful that looks. When we get there. All right. So I made a small mistake. This isn't very easy to look at because it's on a regular scale. It's not on a log fold change. So I'm gonna change the base mean to a log 10, and that should smooth this out a little bit. Right, so that looks better. I have NAs. I still have stupid NAs in here. I forgot to remove my NAs. So there is this weird property about DESeq that in some cases, if it really can't do a very good stats test, it's just going to populate p-value and p-adjusted with NAs, like not applicable. Basically means it really wasn't tested, or the parameters weren't met for it to be tested. Like there's a serious outlier or something along those lines. So there's something I forgot to do, and that's to remove the outliers. And so I can remove the NA omits. I can remove the NAs. That's what I can do, and that's really not that bad to do. I'm just gonna DESeq res is equal to na.omit that DESeq res. Okay, let's try this again. And so that should have, that gets rid of about 1,000 data points. About 1,000 data points in this data set were NAs, right? So I don't care about the NAs, so I just get rid of them, right? So now this should look familiar. We've kind of made this plot before with plot MA. That's part of the DESeq package. But in this case, we have it with a significance for blue or red. We can always change colors in ggplot, but I'm not going to worry too much about that because to me that's just a detail. But again, we can replicate the plot MA function of DESeq to identify which genes are, to demonstrate that there are differentially expressed genes in all of this among all normalized read counts, right, across that entire range. As long as there's above 10 read counts, we'll see some differentially expressed genes. And we can express this plot in a slightly different way. That's called a volcano plot. Now, I haven't seen volcano plots in kind of quite a while, but they are helpful to distinguish that there are significantly differentially expressed genes throughout here. So we can make that plot real quick. So I'm just going to kind of label this plot MA and then a volcano plot. And so on a volcano plot, we're just really changing the X and the Y. As DESeq, we're still using the same data frame. It's just the AES where the X is going to be the log full 2 change or log 2 full change. And Y is going to be something a little bit weird. It's going to be a negative log 10 of the P adjusted value, P80J. And then again, still color on the sig. And plus, we'll do a plus G on point, still a G on point. Hopefully that won't complain. All right, and so this is what we will call a volcano plot. It's not a bad representation. I don't see it very often, but what we're basically doing is it kind of like we're looking at the p-value and association with the log full change more so than the base mean, right? And so if we kind of see what's happening to the p-value whenever we do this transformation, this log full transformation, we can kind of see what that looks like for a second. So let's just have some pseudo p-values. I'll start with 1 and kind of decrease to 0.5 to 0.05 to 0.05, 0.0005, and one more, 0.02345. All right, so we have these pseudo-esque p-values, in which case, if I take the log full 10 of this, or a log 10 of this, equal log 10 of that. All right, it's going to be 0, whatever. But I'm going to take the log 10 of all these others. Okay, and we notice that really whenever we're doing this, we're really plotting out like the log 10 fold change of the p-value. Right, so this decreases, we're at 0, then negative 0.3, and then 1.3234. So this 1, 2, 3, 4 basically tracks the number of zeros that are present in this decimal number, right? 0, 1, 2, 3, and 4. But it's on a negative scale. So we can fix that by just taking the negative of that. Equals the negative of this number. And we can redo this, and it basically turns everything positive, right? So that's what we're doing whenever we take the negative 10 or negative log 10 of a p-value, is it turns it positive, and it lets us know how many decimal places that p-value has, right? How many? So that's what we see whenever we're seeing here. It's like one of these p-values. We have like 30. It's like times 10 to the negative 30 plus as a p-value. So that's one of the more differentially, or at least that's one of the highest p-values or the lowest p-values in this whole data set. It's pretty massive. And then of course we have the log fold change on the x-axis, right? And again, if we think negative, whenever it's negative, it means that the gene is more expressed in salt water. If it's positive, the gene is more expressed in fresh water, right? And so we still kind of see this pattern, right? It's the same data, right? It's effectively, it's more or less the same plot, right? Our plot MA and our volcano plot are more or less displaying the same thing, right? If our more genes are differentially or higher expressed in water treatments than genes that are in saltwater treatments. That trend is constant. But let's kind of visualize this in one more way that's taking advantage of heat maps. So I really like heat maps to display matrix data. And so our normalized recount. So in this case, instead of looking at the fold change or the p-values, we are going to look at the normalized recount data. And specifically, I really only care about the recount data of the significantly differentially expressed genes. Now, I will add one more point, like depending on the author, depending on the study, depending on the situation, they may add an extra criteria to say that the log fold change has to have an absolute value greater than 1, and the p-adjusted value has to be less than 0.05. But I'm not worried about the log fold change, and again, it's just kind of a detail that we really don't need to worry about. We're just worried about the 0.05. We're worried about the significant or the adjusted p-value. So again, we're going to look at p-heat map. But I have to manipulate this data a little bit. I have to manipulate the recount data a little bit. And I'm not that great with R. I do what I can, but I'm certainly not the most versed in what R can do. But nonetheless, some things that I want to do first. So first of all, I only care about the genes that are differentially expressed. So I'm going to filter out this DESeq results file. I'm going to filter out everything that has a p-value greater than 0.05 because I don't want that. I want to keep anything less than 0.05. And so I can use this function subset. This is a base R function to do so. There are other things in like the tidyverse that can help. What am I calling this? What do I call this? DESeq res. P adjusted less than equal 0.05. And so whenever I do this, it's just, if I just run this by itself, we should see it happen. It's just going to get rid of all the p-values that are greater than 0.05, right? So the sig should always be yes in this column. Fine. So I need to save that. I'm just going to save this as, I'm just going to say it's signi. Stupid. Okay, right, and so now if I look at signi, it's just the significantly differentially expressed genes in this data set. Now, furthermore, I can merge my data sets. So I can merge DESeq and norm recount, or I can merge signi and norm recount, because both of them have the column names are the same, or sorry, the row names are the same in both data frames. So I can filter and basically merge these two together. Wherever signi, whenever there's a gene for signi or the row name for signi is present in both, print it back out. So again, there's probably an easier way to do this, but I'm just familiar with the base, what our base can do. And so that function is merge in ERG. And so merge is like we're going to call both data frames and then what condition we want to merge them by. So that's going to be norm count signi, and by is equal to 0 just means that we're merging by the read count, or sorry, merging by the row name. So I'm going to call this something else. That's just all sig. Okay, so now we have this third, or really fourth data frame. And in this data frame, right, we have the row names go away. We get a row name as a variable or as a column name instead of the actual row names. We can fix this in a second. But then we have all the normalized read counts that we find in norm count, and then all the columns that we would find in the DESeq or the signi data frame, right? So all that stuff more or less got pushed together into one data frame. But then there's, so p heat map really only wants a data frame that has your the normalized read counts in it. So really I only need the first 1, 2, 3, 4, 5, 6 columns, right? The read count columns. Those are the only ones that I really need for doing a p heat map. So I have to get rid of all the other things. And that's, again, just all I know is the base R thing to do. And that's just taking advantage of what R can do. So that's going to be all sig. And again, I only want the 2nd to 7th columns, right? I don't want the first column just yet. Yeah, I don't want the row names column yet. I just want the real read counts, the normalized read counts that are found in columns 2 through 7. And so whenever we use like these square brackets, it's more or less kind of a matrix. So anything to the left of this comma, we're asking for, I believe, the row names. Nope, columns. So left of this number, left of this comma, we can denote column numbers. So that would be like 1st through 7th rows. I'm confident it's rows, 1st through 7th rows. Whereas on the right hand, we're basically saying what columns do we want, and that might be 1 through 7, the 1st through 7 columns. So I want all the rows, so I'm going to leave that alone, and I want the 2nd through 7th column. And if I just run that, it should just return all of the read count information for this. And I'm pretty confident that worked. Yes, I don't have the row names. And so I'm going to call this sig counts. Right, getting a p heat map ready probably does take a little bit more time than anything else. But I still want those renamed. I still want those column names, or I want those row names. I want the row names. So I want the row names to also be involved in my sig counts. So I can do row.names of the sig counts is equal to signi $row.names. That should be fine. I got grumpy. Signi, what's happening? I didn't do this. Row names. What am I looking for? I want signi. I want, what was? I want all sig. That's right. I want all sig. That's it. I want all sig. My mistake. Oh, now we're getting in trouble. Something's going wrong. Because row name is not a function, but row names is. That's the problem. There we go. And so now if I look at all sig, or sorry, I should look at all sig counts. Sig counts. Sig counts. There's sig counts. So now I have the row names back with the gene, with the appropriate gene name, plus the read count data. All right, now we're ready for actually p-heat map. So p-heat map is actually a pretty nice function to use. It's actually it's pretty nice. It's a very nice library for making p-heat maps. So it's pretty easy to use. This is going to look like trash for a little while, but I'm kind of making a point about heat maps first. So really the raw thing that you have to do with p-heat map is just call the function p-heat map and the matrix. So this would be sig counts. And that's going to give me a figure. It's just going to look like trash at first. Right? So what it's going to do is it's going to give me the expression value. So again, what I'm doing is just presenting these numbers, these expression numbers, or these normalized read counts as a color. And this color is going to range from blue to red, where blue is low, red is high. Now the annoying thing about read counts is that it is on a log scale, right? It's on a log 10 scale. You'll see stuff expressed with read counts that are in the thousands or dozens of thousands, and you can see read counts that are in the zeros to tens. And so if you have one gene that's expressed has a read count of like 300,000 or 30,000, something ridiculous, you won't be able to see the expression of the lowly expressed genes. And so that's what we're seeing here. There's one gene that's really highly expressed, and it basically washes everything else out. Looks like garbage. So we can address that one step further by normalizing this read count data. And so we can normalize using a log2, right? Log2 is a really common way. It lets us look at the exponents instead of the raw numbers, right? How the fold changes. So I'm going to look at the log2 of this. And if I do just a log2, I'm probably going to get grumpy. This is probably going to get grumpy because if I do a log2 of a read count and a read count is 0, it's going to give me an NA. So I have to transform this in one step further to do a log plus 1, because a log of 1 is 0. So you're really not affecting the data all that much by doing a log plus 1. And so when we do that, it scales out a little bit nicer. So now we can actually see which genes are highly expressed and which genes are lowly expressed, as opposed to the raw read counts. We're looking at the log2. Basically the exponent. But this is still not exactly helpful to see how these genes are differentially expressed. So we can do this one step further in p-heat map. There's a function called scale. And so scale lets you basically compare expression within a column or within a row. And so I'm going to do scale by row, in which case what's going to happen is it's going to find the median read count or the log transform read count of a row. Right? It's going to find that, it's going to find the mean, and it's going to find the distribution, so you more or less have a standard error or a standard deviation. And so whenever we scale, instead of looking at the raw numbers, we're looking at where this data falls, where a data point falls in the distribution. We're going to use like a standard deviation to do so. Hard to explain, much easier to visualize. Okay, now it's basically we scale by row, and within this row we know which genes are higher and which are lower. That's what scaling by row means. Is we're ignoring if one gene is expressed or has an expression of 15, right? Our log expression is 15, and we have another one that's 2, right? It still gets kind of washed out. And again, we really can't see the differentially expressed genes. We just see what are high and what are low. But if we scale by row, then we can really see where the highly expressed genes are and where the lowly expressed genes are. And again, this kind of demonstrates, if we see orange, these genes are highly expressed in this row, and if they're blue, they're lowly expressed. And again, we kind of still see this same trend. We see this exact same trend that more genes, if they're differentially expressed, they're higher expressed in water treatments than in saltwater treatments. Only a fraction of them we see an increase in expression compared to a regular tap water treatment. All right. So again, I like heat maps because they let us see how the data changes. Right. It's a transforming these numbers into a color, and the colors are a lot easier to see. But there's additional garbage in here, like the row names isn't very helpful. But row p heat map lets us manipulate that. I think we can get rid of show row names is equal to false, and that'll get rid of row names. That makes it look a little bit nicer. And we can also get rid of these trees. So the dendrograms are pretty helpful, right? I mean, they demonstrate clustering, right? The genes in saltwater are a little bit different than the genes in freshwater, or the expression is a little bit different. And so we see that dendrogram clustering our columns, which is fine. Clustering the rows is kind of fine. It helps us differentiate where this shift is in high to low. Fine. But I don't necessarily like them being there, so I can kind of get rid of that. I think tree height row is equal to 0. That should get rid of the rows, and tree height column is equal to 0. We'll get rid of the dendrogram. So now all we have are this z-score. It's really a z-score, and the z-score basically tells us where in the distribution this data point falls, and we use a standard deviation or the standard deviation to reflect that, right? But the point being, if it's red, it's near the high end. If it's blue, it's low. Right, so I can certainly save that if I so wanted to, export it as a PDF or PNG, and there we go. Right, so we have our differentially expressed genes. And we can visualize that they're differentially expressed and how they're differentially expressed. So I'm going to leave it there for visualizing. There's certainly more than that we can do to visualize differentially expressed genes or not. But I'm going to leave it there. And kind of the next step is to see if these genes that are differentially expressed are in specific pathways, right? If they're in specific metabolic pathways or biochemical pathways. If there's a common function around these genes that are differentially expressed. And so that I'll tackle on Monday, and leave it at that. All right, until then, I'll see you later.